Space is quiet. It is a vacuum of infinite silence, cold enough to shatter steel and hot enough to boil blood. For all of human history, we have looked up at the moon, that pale, ghost-like companion in the night sky, and we have dreamed of walking on its surface. And eventually, we did. We crossed the void, we left our footprints in the gray dust, and we planted our flags. But then, we did something strange. We left. For over 50 years, humanity has remained a mere visitor in the cosmos. Even on the International Space Station, a marvel of engineering that floats above our heads, we are effectively just camping. We live in aluminum cans, thin-walled modules built on Earth and launched atop massive pillars of fire. We bring our air, our water, our food, and most importantly, our shelter with us. We are tethered to our home planet by a very long, very expensive supply line. We are fragile. If we are to change this, if we are to transform from visitors into a true spacefaring civilization, we need a radical new approach. We are about to uncover the technology that will build our future among the stars. But before we launch into the details of this lunar revolution, if you enjoy exploring the deepest questions of the cosmos and the future of humanity, please take a moment to subscribe to the channel and hit the like button. It supports the channel immensely and ensures you never miss a journey into the unknown. Now, back to the problem. Why haven't we built a base on the moon yet? The answer lies in the cruel mathematics of space travel, specifically something known as the tyranny of the rocket equation. Gravity is a jealous landlord. It demands a heavy tax for everything you try to lift into orbit. To launch a single kilogram of payload from Earth to the lunar surface costs tens of thousands of dollars. To ship enough concrete, steel, and glass to build a simple 3-bedroom house on the moon would cost more than the GDP of entire nations. It is logistically impossible. The harsh reality is that we cannot bring civilization with us in a suitcase. If we want to stay, we cannot rely on Earth for our walls and our roofs. We have to do what every pioneer in history has done before us. We have to live off the land. This concept is called In-Situ Resource Utilization, or ISRU. It sounds like a dry technical term, but it represents a philosophical shift in human history. It means we stop acting like tourists who bring their own tent, and start acting like settlers who build with the earth beneath their feet. NASA, working with cutting-edge construction technology companies like Icon, has launched an initiative known as Project Olympus. The goal is audacious but practical. To send a robotic 3D printer to the moon, land it on the surface, and have it build critical infrastructure before the first astronaut even arrives. The dawn of the lunar mason. To understand the genius of this solution, we must first respect the enemy. And on the moon, the enemy is the ground itself. The moon is covered in a layer of loose soil and rock called regolith. But calling it soil does it a disservice. On Earth, wind and water erode sand into smooth, round grains over millions of years. It's soft. It flows. On the moon, there is no wind and no water. The grains have never been smoothed down. They remain jagged, sharp, and abrasive, like microscopic shards of crushed glass. During the Apollo missions, this dust was a nightmare. Apollo 17 astronaut Harrison Schmitt described it as smelling like spent gunpowder. It clung to everything. It abraded the outer layers of their spacesuits, it scratched their helmet visors, and it clogged the seals of their equipment. It is dangerous to breathe and difficult to handle. For decades, engineers viewed regolith as a nuisance, a hazard to be avoided. But Project Olympus flips the script. It looks at this deadly, abrasive dust and sees it not as a problem, but as the raw material for our survival. Imagine a machine, not a humanoid robot walking on 2 legs, but a massive, spider-like gantry system, designed to withstand the harshest environment imaginable. It lands silently on the lunar surface, perhaps in the eternal light of the Shackleton crater near the lunar South Pole. There are no humans around to guide it. It is autonomous. It begins to crawl across the gray landscape, scooping up that sharp, abrasive regolith. On Earth, a 3D printer typically uses a nozzle to squeeze out plastic or wet concrete. But on the moon, water is more precious than gold. We cannot waste it on mixing cement. Even if we could, the water would boil off instantly in the vacuum. Instead, this robotic mason uses a process known as sintering. Using a high-powered laser or a focused microwave beam, the robot heats the lunar dust to over 1,500 degrees Celsius. At this temperature, the physics of the material changes. The jagged, glass-like grains melt and fuse together. As the robot arm moves with mathematical precision, it lays down a bead of molten rock that quickly cools and hardens. It doesn't need glue. It doesn't need water. It uses pure heat to transform dust into solid rock. It is creating a ceramic material that is potentially stronger than reinforced concrete on Earth, derived entirely from the moon itself. Layer by layer, the structure begins to rise. But these won't look like the houses you see in your neighborhood. We have to forget everything we know about Earth-based architecture. You won't find sharp corners, flat walls, or pitched roofs here. In a vacuum, the air inside a habitat pushes outward with immense force, 14.7 pounds per square inch. It wants to explode the building like a balloon. Sharp corners create stress points where this pressure can tear the structure apart. Therefore, the architecture of the moon is the architecture of curves. These robots will print domes, arches, and catenary shapes. These are designs that distribute stress evenly throughout the structure. They will look organic, almost like termite mounds or ancient igloos rising from the gray dust. But there is another reason for this shape: radiation. The moon has no atmosphere and no magnetic field to protect us from the sun's fury or cosmic rays from deep space. To live there safely, we need shielding. These 3D printed domes are designed to be strong enough to support a thick layer of loose regolith piled on top of them. We are essentially building high-tech caves. The robot prints the shell, and then buries it in dust. This blanket of rock protects the fragile human occupants inside from radiation, thermal swings, and micrometeoroids. The implications of this technology extend far beyond just sleeping quarters. If we can print a habitat, we can print a civilization. One of the most critical things we need is a landing pad. Currently, when a rocket lands on the moon, its exhaust plume is a violent event. It blasts dust and rocks at incredible speeds, essentially sandblasting everything in the vicinity. This ejecta can travel for miles in the low gravity, threatening other landers, rovers, or habitats. Without a proper landing zone, a lunar base is constantly at risk of being destroyed by its own supply ships. A 3D printed landing pad, baked from the lunar soil itself, solves this problem. It traps the dust. It provides a stable surface. We can print blast shields to protect equipment. We can print roads to keep the dust down as rovers travel back and forth. We are effectively paving the way for our own arrival. Of course, describing this is easy. Doing it is one of the hardest engineering challenges humanity has ever faced. We are talking about operating heavy machinery in an environment that tries to kill machines. The lunar cycle is brutal. The lunar night lasts for 14 Earth days. During this time, the sun vanishes, and temperatures plunge to -170 degrees Celsius. Then, the sun rises, and the surface bakes in searing heat. This thermal cycling causes materials to expand and contract violently. On Earth, this cracks pavement. On the moon, it can tear a robot apart. These machines must be robust. They must be able to sleep through the freezing night and wake up when the sun returns. They must operate autonomously, with a delay in communication from Earth. If a nozzle clogs, or a motor seizes, or a sensor fails 384,000 kilometers away, there is no repairman to call. The machine must be self-correcting and nearly indestructible. NASA is currently testing these concepts on Earth. At the Marshall Space Flight Center, they used simulants, fake moon dust created to mimic the chemical and physical properties of the real thing. They are testing the lasers, the microwaves, and the robotics in vacuum chambers. They are running the tape forward, simulating the harsh conditions to ensure that when we finally break ground on the moon, the walls will hold. And here is the bigger picture. The moon is not the final destination. It is a proving ground. It is a sandbox. Everything we learn about 3D printing on the moon, how to handle the dust, how to operate autonomously, how to build with local resources, is practice for the real prize, Mars. Mars is further away, the communication delay is longer, and the environment is different. But the principle is the same. If we can prove that we can build a home on the moon using nothing but robots and dirt, then we prove that we can build a colony on the red planet. We are developing the toolkit for becoming a multiplanetary species. It represents a fundamental shift in our relationship with the cosmos. For thousands of years, we have looked at the moon as a light in the sky, a poetic object, a god. Now, we are looking at it as a construction site. If Project Olympus succeeds, the first permanent human structure on another world will not be built by human hands. It will be built by a silent, solitary robot, tracing lines in the dust under a star-filled sky, working tirelessly in the vacuum. When the astronauts finally arrive, perhaps on an Artemis mission later this decade, they will not be stepping into a cramped, temporary lander. They will be walking into a home that belongs to the landscape. A home born from the moon itself. This image forces us to reconsider our place in the universe. We are often told that space is empty, dead, and uncaring. And perhaps it is. But it is also filled with the raw materials of potential. It is waiting for us to shape it. The Earth is our cradle, but as the visionary Konstantin Tsiolkovsky famously said, one cannot live in the cradle forever. To leave, we must learn to build. And it seems that our future among the stars will be built one layer, one laser beam, and one grain of dust at a time. Thank you for joining me on this journey into the future of construction. If you found this video fascinating, please let me know in the comments. Would you live in a 3D printed house on the moon? Don't forget to subscribe and click the bell icon so you're notified of our next deep dive into the universe. We have so much more to explore. Until next time, keep looking up.